So let's continue to look at DAGs, and in this section we'll look at a different problem called identifying the longest path in a DAG. So recall that a directed acyclic graph is just a directed graph in which there is no directed path from any vertex back to itself. So it is directed and it is acyclic. Any directed acyclic graph can be topologically ordered. If we think of the vertices as being 1 to n, we can write out 1 to n in a sequence in such a way that for every pair jk which is an edge, if jk is an edge in my graph, then j will appear before k in the sequence. So if we think of these as tasks with dependencies, it means that I can do the task in such a way that before I do k, I would have finished its dependent task j. Right? So this is called a topological sorting. So let's look at a different question about DAGs. So supposing we have this DAG and we imagine that the vertices represent courses and the edges are prerequisites. Now these are courses that we have to do to maybe complete a degree. Every course requires a semester, but we can do more than one course in a semester. So the question is, what is the minimum number of semesters that I need to complete this program consisting of these 8 courses with these prerequisites? So clearly I can start by doing courses 1 and 2 in this first semester because they have no prerequisites, so they can be done immediately. Now having done 1 and 2, I can do 3 because 3 only depends on 1 and 2. Similarly, I can do 4 and 5 because they depend only on 1. Now 8 depends on 1 and 2. I need the material, or at least it depends on 2. I need to have done 2 to do 8, but I still cannot do 8 because it also requires 5, 4 and 7. So at this point, the only courses which are available are 3, 4 and 5. So in my second semester, I can do 3, 4 and 5. Now the only course for which all prerequisites are satisfied is 6 because 7 requires 6 which has not been done and 8 requires 7 which has not been done. So in the third semester I'm stuck with doing only one course, namely 6. In the fourth semester I can do 7, and finally after 5 semesters I can complete these requirements. So in general we can ask this question, okay, if I think of these as DAG as representing courses, what is the minimum number of semesters? Now this problem corresponds to asking for the longest path in the DAG. What we are saying is that it takes 5 semesters to complete 8 because there is a chain of dependencies where 8 depends on 7, 7 depends on 6, 6 depends on say 3 or 4, it doesn't matter which one we choose, and 3 depends on 1, and this chain forces us to spend 4 semesters because there is a chain of length 4 semesters before I can do 8. Notice that it is not the shortest chain because there are shorter chains. For example, 8 to 2 takes us back to a vertex which has in degree 0. But this doesn't help us because after 2 I cannot do 8. So I must wait for everything that has to happen before 8 in order to get the job done. So unlike other problems where we might be looking at shortest paths, here we're actually interested in the longest path. So we can set up this problem as follows. So we can say that for any vertex which has in degree 0, the longest path to that vertex is of length 0 because I can do it immediately. And on the other hand, if I have a vertex whose degree is not 0, then it has some incoming edges. So I have a vertex k. Right? So I must wait for all of these to finish and then do it. So if I take all of these, I have to take, among all of these, I have to take the maximum length because that will be the last thing to finish, and after that I have to do plus 1 to account for k. So if the degree is not 0, then the longest path to k has length 1 plus the maximum of the longest path to all its incoming neighbors. So therefore, in order to compute the longest path to k, I need to compute the longest path to all its incoming neighbors. Now if we have arranged the vertices in topological order and we compute the longest path in that sequence, then when we get to k, every incoming neighbor j will be on its left. Hence, we would have already computed its longest path, so we would be able to take the maximum of all of those and add 1. Right? So by sorting this vertices in topological order, I can then compute the longest path in the same order with the guarantee that when I want to compute the longest path to a given vertex, I have all the information available needed to do that, namely all the longest paths for its incoming neighbors. So if I do it naively, right, then I will write out my vertices in some topological order. And now when I come to this vertex and I want to compute its longest path, I will look at in my graph all the incoming edges, and they will all be from vertices which appear before. So I can take the value here, the value here, the value here, and then take its maximum and then add one. Okay. So actually we will see that you don't need to do this backwards, you can actually do it forward. So we can actually incrementally compute the value at ik as we are going forwards, because going backwards requires to scan this list and look for all the incoming neighbors. So we will kind of implicitly do this longest path calculation along with topological sort side by side, as we will see in the next example. So here is an example in which we are going to compute the longest path as we are computing the topological order. So as before, the red numbers against the vertices are used for topological sort, and they denote the in degrees, right? So the initial in degrees are given by the initial edges in our graph. And what we do is we compute the longest path incrementally by starting by assuming that the longest path to every vertex is actually 0. Now when we enumerate a vertex in topological sort, what we did earlier was to update the in degrees, right? So this is something that we already did. But now the additional thing that we do is we say that, well, if the vertex 1 had to be enumerated before 3, 4 and 5, then among the values that I know for the incoming edges of 3, 4 and 5, 0 was the maximum length, so I must do 1 plus that. So these paths are at least of length 1. So the longest path to 3, 4 and 5 is at least 1. Okay. Now if I enumerate vertex 4, okay, then its longest path is at least 1. So therefore the longest path to 6 must be at least 1 plus 1. Similarly, the longest path to 8 must be at least 1 plus 1. And of course the in degrees will also reduce as before. So the in degree of 6 goes down to 1, the in degree of 8 goes down to 3, but the longest path to 6 is now the longest path to 4 plus 1. So it is 2, the same with 8. Now supposing I enumerate vertex 2, okay. Now 2 will again say that the longest path, because of 2, the longest path to 3 is 1, but it's already 1, so we don't change it. This will say because of 2, the longest path to 8 is at least 1, but we know it's at least 2, so again we don't change it. So when we delete a node, then we take basically the current value of the longest path for its outgoing thing plus 1, or the current value of the deleted node plus 1, and what is already known about that node, and we keep the maximum. So in this case, this 1 will become 0, this 3 will become 2, but here there is no change, and here there is no change. Okay? Now likewise, when I remove this 5, this 2 will become 1, but because 1 plus 1 is 2 and we already know that 8 has a longest path of at least 2, we don't make any change in the 2. Now when we go to 3, 3 says it has a longest path of 1. So therefore, because of 3, the longest path to 6 is at least 2, but we already know it's 2, so again there is no change. Now we should do something interesting. So we say that 6 has a longest path of 2. 7, we so far have believed it has a longest path of 0, but through 6 it has a longer path. So the path to 7 must now be updated from 0 to 3. And now because of this, when we go from 7 to 8, the longest path for 8 must be updated from 2 to 4. Okay. And now finally, this is my last vertex, so I just enumerate it and I compute its longest path as 4. So what this has said is the longest path is 4. Now we said that it would be done in 5 semesters, the same example, which basically means that in the first semester all those whose longest path is 0, the second semester all those whose longest path is 1, and so we have the same sequence you had before. So we initially do 1 and 2 in the first semester, then we do 3, 4 and 5 in the second semester, then we do 6 in the third semester, 7 in the fourth semester, and 8 in the fifth semester. So this is exactly the solution that we obtained informally on our initial example. So the pseudocode for longest path, as we saw, is very similar to what we did for the topological sort. We just have to keep track of this extra longest path value. So when we initialize the in degree, we also initialize the longest path to I to be 0 for every vertex. Okay? So this we are doing again first the adjacency list version. So we do n square work, right? For each vertex, we compute the in degree by looking at the column of the adjacency matrix with column entry I. But we also update, we initialize longest path to each I as 0. Now when we are doing this enumeration, as before we choose any vertex with degree 0, we enumerate it and we update the degree of this vertex to -1, so it is no longer in contention for being chosen again. Now for all its outgoing neighbors, we update the degree and we also update the longest path. So we take the longest path that we already know to that neighbor, LPT of k, and we take 1 plus the longest path for this node, and whichever is larger, we replace that back in LPT of k. So it's a very simple variation of the basic topological ordering thing, which allows us to also compute the longest path. Right? So this has complexity order n square, for the same reason that we had found that topological sort with adjacency matrix as order n square, because we have these nested loops in order to scan all the neighbors. So as before, we can update this whole thing using adjacency lists and a queue to make it a linear time algorithm. So if you go back and look at the topological ordering algorithm, you'll find that the same changes are required to make it additionally compute the longest path. So what we do is initializing is again the same. We do it for every vertex. So this is an order n step. Right? We initialize both the degree and the longest path. Then we go through all the adjacency lists, and together this is an order m step to compute the initial degrees. And now we have an order n step in order to set up this queue where we will process the topological ordering. And then we do an outer loop of order n. Okay, so this is an order n loop because everything is going to go into the queue once and come out. So we are going to remove from the queue n times. And now, because we are scanning the list across all the n iterations, we are going to process each edge once. So the total work done in this loop is going to be order m. Right? So we do exactly as before. We update the degree. We update the longest path to k as the maximum of the current value plus and 1 plus the value of the current node. And if we do find that the k has now become a vertex with degree 0, we add it to the queue. So DAGs are very useful because there are many situations where we want to model dependencies between various objects. And topological ordering is a canonical algorithm to list out vertices without violating dependencies. And what we have seen today is that we can compute the longest path in a DAG, okay? And the longest path in a DAG, in some sense, if we can list out vertices in groups, the longest path in a DAG represents the minimum number of steps in order to enumerate all the vertices. So if we can do courses in groups, then if we want to bunch it and do things which are at the same level at one time, then the minimum number of steps we need, then a minimum number of semesters to complete a set of courses, or the minimum number of days to complete a set of tasks, okay, is given by the longest path. Now it is important that we have been able to find an efficient linear time algorithm for longest path only because we restricted our attention to DAGs. If we look at arbitrary graphs, which are not necessarily DAGs, and we want to find longest paths, of course, if we have loops, the longest path will be undefined because we can go around and around a loop. So if we define a longest path to be one in which we have a sequence of vertices with no duplicates, so the length is at most n, okay, then in an arbitrary graph, this is a very challenging problem and there is no known efficient algorithm. In fact, it is part of a group of highly intractable problems which are all equivalent to each other and all believed to be very hard. So DAGs are a very significant subclass of graphs which have many practical applications and which admit efficient solutions for very important problems which are not in general solvable easily on the full class of graphs.